Okay, so we just saw how to calculate confidence intervals for dependent samples. Confidence intervals for independent samples have just two key calculation differences. One, the standard error uses the variance and the sample size from both samples. And two, the degrees of freedom for the t-score or critical value also consider the sample variances. So it's no longer just sample size minus 1 to get the degrees of freedom. But that's it though. So if we look at the formula for the confidence interval for independent samples, which would have scared us in the past, we now know that it's just two components. We have a point estimate, which in this case is the difference in the sample means, and we have a margin of error, which as always is made up of a critical value for the confidence level, in this case using the t-distribution, since we're assuming that we don't know the population standard deviation, and a standard error. And as you can see in this scenario, the standard error is using s squared for each sample here, and if s is the standard deviation, then s squared is the variance. And then it also uses the sample sizes as well, which is the n here. All of which we know how to calculate though. So the only thing that's going to get a little bit tricky is calculating the critical value. In the past, we've used t.inv. We'd provide alpha divided by 2 or 1 minus alpha divided by 2. And then for the degrees of freedom, we only just did n minus 1. But here we need to calculate the degrees of freedom using this formula. Now, I know that this looks scary and intimidating, but trust me, it's using values that we know how to calculate, the sample variances and the sample sizes. And we're going to structure our Excel workbook in a way that's going to make it easy to plug these numbers into this formula, so don't worry. Now, important call out here, you might see independent samples divided into separate calculations if the population standard deviations can or can't be assumed to be equal between them. But this formula works for both scenarios, so no need to worry about that. And shout out to Mike Gervin from Excel is Fun for showing this one in one of his YouTube classes. So now that we know all this, let's head over to Excel and apply it to our project. So here in Excel, I'm going to go to the link on independent samples. And we want to know if business undergrads achieve higher MBA grades on average than the rest. And this is something that we've looked at in the past when calculating the descriptive statistics for our sample of students, but we want to see if we can expect the difference to apply for the entire population. Because if so, it may be something that requires some sort of action from our school. We either offer some preliminary courses to the other undergrads to help bring their grades up, or think about giving a higher preference maybe to business undergrads in the recruitment process. So let's calculate this confidence interval. We have our two populations of independent samples, and we know they're independent because we can't form any pairs between them. So let's calculate the sample statistics for each one. We're not going to calculate the difference and treat it as a single population. So the sample size is just a count. You'll see that we do have different sample sizes in this scenario. I'm also going to calculate n-1 and eventually variance divided by the sample size, just because you'll notice that these components live in the formulas that we're going to be using, so it's going to make it easier to plug them in later. So this is just n-1. Apply this to the right here. Now we want the mean. And the variance of the sample. And finally, the variance divided by n. So this divided by this right here. Apply it to the right. And we have our sample statistics. Now our point estimate is going to be the mean of the business undergrads minus the mean of the other undergrads, since we want to see if we find a positive difference between these two. So if we can confirm that business undergrads have higher grades than other undergrads, we'll see that we do get a positive point estimate of 1.9. So in our sample, business undergrads do have a higher average than other undergrads. Now let's add the margin of error on each side, starting with the confidence level. Now I want to take a minute to think about this, because how sure do we need to be that business undergrads get higher grades on average in order to take any of the actions that I outlined? So either offer the preliminary courses for the other undergrads, or maybe give higher preference to the business undergrads. I think in this case, I'd be comfortable with a 10% chance of error or 90% confidence level. So let's do that. Anything less, I think we should just stick with what we're doing right now. So let's calculate our confidence interval with a 90% confidence. That gives us an alpha of 10% and an alpha divided by 2 of 0.05. And this is where we typically go ahead and calculate the critical value, but we need to calculate the degrees of freedom for our critical value before that. And we're going to use this formula here. So let me open a parentheses. We want the variance divided by the sample size of the first sample, which is this right here, plus the variance divided by the sample size of the second, which is this. And we want to square that. And then we want to divide that, let me open up another parentheses, by the variance divided by the sample size squared, divided by sample size minus 1, which is this right here, and then plus variance divided by sample size squared for the second sample, which is this. Let's square that, divided by the sample size minus 1. Close our parentheses, press enter, and we get 66.53 degrees of freedom. Technically, we need to round these to an integer, but the t.in function will actually do that for us. So we can just leave it like that. Now we can calculate our critical value, the probability. I'm going to do 1 minus alpha divided by 2, and use these degrees of freedom for our t-distribution. Press enter, and we get a critical value of 1.66. Now for the standard error, we need to use this formula. So square root of the variance divided by sample size of the first sample plus the second sample. Press enter. We get a standard error of 1.34. And then for the margin of error, we just multiply the critical value by the standard error, and we can calculate our confidence interval. So point estimate minus margin of error, and point estimate plus the margin of error. So what does this confidence interval tell us? Well, that we can be 90% confident that the mean MBA grades for business undergrads are between negative 0.4 and 4.1 points higher than the rest. In other words, we can't be 90% confident that they are higher on average, since this interval includes negative numbers. For all we know, the actual difference in the population means could be negative 0.2 or it could be 0. So there's no need to take any immediate action here, even though the sample originally suggested that we should. And that's the power of statistics. Alright, time for an assignment on confidence intervals for independent samples. Nick is back with a fresh question. He wants to know, can we find a positive difference in the employability scores for graduates that have been placed so far versus those that haven't? I think sticking with the same 90% confidence should work. Alright, so let's break this process down into some key objectives. Number 1, calculate the mean and variance from both samples. Calculate the point estimate, or the difference in sample means. Calculate the margin of error, and then set the limits for the confidence interval. Time for the final lecture from this section, and I'm going to keep it as a pro tip since it is using the same concepts that we've already covered throughout, with just a few minor tweaks in the formulas. So by now we've seen the difference in population means, but you can also calculate confidence intervals for the difference in population proportions. Now the formula looks like this, which as always, you'll have a point estimate, in this case the difference in sample proportions, plus minus a margin of error, which is going to be made up of the critical value for the confidence level. In this case, you'll notice that it does use the z distribution, so there's no crazy formulas for the degrees of freedom. And you also have the standard error. So let's do a quick example together in Excel. I'm going to go to the final link from the confidence interval section on difference between population proportions. And in the previous lecture, we saw that placed graduates have higher employability scores than graduates that haven't been placed. So what we want to know now is if graduates with previous work experience are placed at a higher rate. So let's calculate the sample statistics here. The sample size for students with work experience is going to be count ifs. So like these, fix that range. So we want to count the students that have yes here. Apply this to the right. So we have yes and no. Again, this adds up to the 95 total students in our first graduate class. And now for these students with work experience, we want to see the proportion of them that was placed. So we want to count ifs, the number of students with work experience, in which the status here is placed. And that's going to return the count of students that were placed with work experience. We want to divide by the total number of students with work experience, which is this. Press enter. You get a proportion of 0.73, so 73% of the students with work experience have been placed, and only 50% of the students without work experience have been placed. Now 1 minus p. Let's do that for both. And we still need to check if the central limit theorem applies for both of these samples. So we want to do p times n, drag this to the right, and then 1 minus p times n, drag that to the right. We get all values greater than 5, so we are good to go. Now let's just calculate our point estimate, which in this case is going to be the proportion of students with work experience minus the proportion of students without work experience. And we get a quite positive point estimate of around 23%, so that does suggest that the graduates with previous work experience are placed at a higher rate, but we still need to calculate the margin of error and the confidence interval. So let's start with the confidence level, and we need to think about this. So if we did prove that graduates with previous work experience are placed at a higher rate, then what decisions would we take as Maven Business School? Do we maybe limit the number of students that we admit without work experience? That would be a big call since it could potentially hurt our enrollment numbers. So if we are going to make a decision like that, then we better be certain that we're right. Now, we're never going to be 100% certain, but in this case, let's shoot for 99% certainty. So that's going to be the confidence level. Alpha is 1 minus that, and alpha divided by 2 is alpha divided by 2. Now for the critical value, we're using the z distribution or standard normal distribution, so norm.s.inv, and we want 1 minus alpha divided by 2. That's our critical value. And for the standard error, we have the square root, and I'm going to use the sum function since I'm adding both of these things up. So the first number is going to be p times 1 minus p divided by n. And the second number in our sum is this p times this 1 minus p divided by this sample size. Close the sum function, close the square root function, and we get our standard error. So now for margin of error, we just multiply critical value by the standard error, and we can calculate our confidence interval. So point estimate minus margin of error and point estimate plus margin of error. And would you look at that? Even though our point estimate was so high at around a 23% difference, the confidence interval still dips into the negatives. So we can't be 99% certain that graduates with previous work experience are placed at a higher proportion, which means that we shouldn't modify our recruitment criteria. And here's the interesting part though. Let's say we had gone with a different confidence level, say 95%. Well, if we look at our confidence interval now, our conclusion would have been the complete opposite. So which conclusion is right? Now you're going to hate this answer, but it's the one with the risk that you're comfortable with. That's why it's so important to really put thought behind the confidence level that you're setting. There is no right or wrong, and that's part of statistics. In this case, I would only like to change the application filters that could potentially negatively impact my enrollment numbers if I can at least be 99% certain that there really is a difference and that the placement rates are higher for students with work experience. So something for you to think about as we move on, and it will become more relevant as we cover the concept of hypothesis tests. Alright, time for another project. This time, you are the lead statistician at Maven Pharma, a pharmaceutical company that is in the final testing stage for a new drug to treat arthritis. And you just got an email from Patty Pill with the treatment results. So let's read the email. We have the data from the trial on the new arthritis treatment that we're developing. We had 84 subjects for the trial, 45 which did take the medication, and 43 placebos which didn't but think that they did. So can you use a 99% confidence interval to see if the percentage of patients with marked improvements is significantly higher for those that took the treatment versus the placebos? Awesome. So let's look at the key objectives here. Number 1, check if the central limit theorem applies here and if we can create the confidence interval. Number 2, if it does, estimate the difference in population proportions with a 99% confidence level. And number 3, reach a conclusion from the results. Again, to get started, you can go to the projects folder in the course resources and load up the treatment results workbook. So good luck on this.